Welcome back, students. So in last lecture we looked at the two ways of finding the shape functions for different elements. Today we are going to derive the stiffness matrix for a four noded element for the heat transfer problem. So there are two ways as we discussed last time. So if 1, 2, 3, 4, these are the four nodes, and this is the x axis and this is y axis, this is 0 0, this one is L0, this is LH, and point 4 is 0H. One of the way is to assume that n1 x y is equal to alpha 1 plus, rather write like this, ni equal to alpha I plus beta I x plus gamma I y plus delta I x y, and that really means that n1 for I equal to 1 we have n1 x y will be equal to alpha 1 plus beta 1 x plus gamma 1 y plus delta 1 x y, and we know that n1 has to be equal to 1 at x1 y1. So we have n1 x1 y1, that is n1, and x1 is 0, y1 is 0, and has to be equal to alpha 1 actually, and has to equal to 1. So what we get from here is alpha equal to 1. Now we know that n1 at x2 y2 has to equal to 0. That really means n1 x2 is equal to L, y2 is 0. So that really means alpha 1, which is now 1, so I will write 1, plus beta 1 L plus, now y is 0, so 0 plus 0 is equal to 0. So that tells us beta 1 equal to minus 1 over L. Okay. Similarly, we have n1 x4 y4 is equal to x4 y4 equal to 0. That tells us 1 plus beta 1. So beta 1 is minus 1 over L. So minus 1 over L times x. So x is x4 is equal to 0. So this is 0 plus now gamma. So gamma 1 y is equal to y4 is equal to h. So we write h plus 0 is equal to 0, and that tells us 1 plus 1 plus gamma 1 h equal to 0, and hence gamma 1 equal to minus 1 over h. Similarly, we can find out n1 at x3 y3 has to equal to 0. That really means alpha 1, which is equal to 1, we know, plus beta 1, which is equal to minus 1 over L times x3. Now x3 is L, so write L here, plus gamma 1 equal to minus 1 over h, so we write here, times h is the y coordinate, okay, and then we have plus delta I, or delta 1 in this case, delta 1, and x equal to L and y equal to h. So whole thing has to equal to 0. So what we get is 1 minus 1 minus 1 plus delta 1 LH equal to 0, and that really means delta 1 has to be equal to, so here 1 over LH, okay. So 1 over LH. So what we get? We get equation now. So n1 xy is given by 1 minus 1 over Lx 1 over hy plus 1 over LH xy, okay. So this also we can write it as 1 minus x over L multiplied by 1 minus y over h, okay. Similar analysis we can do for others. For n2, for example, n2 has to be n2 x1 y1 means 0 0 has to be equal to 0, n2 at L0 has to equal to 1, n2 at LH has to equal to 0, and n2 at 0 h also has to be equal to 0. Form of n2 is alpha 2 plus beta 2 x plus gamma 2 y plus delta 2 xy. If you do the analysis same as we did for n1, we can easily find n2 equal to x over L multiplied by 1 minus y over h. Similarly, we can do analysis for n3. So for n3 xy n3 xy, we can find it as x over L multiplied by y over h, and n4 xy, we can find it as one minus x over L multiplied by y over h. Okay. So, here the values for n1, n2, n3 we got by using the solving the linear equations basically. So, there are 4 unknowns, which all unknowns? 4 unknowns. So, alpha I, so alpha 1, 2, 3, 4, then beta I, beta 1, 2, 3, 4, gamma I, gamma 1, 2, 3, 4, and delta I, delta 1, 2, 3, 4. So, there are 16 unknowns and we had 16 equations. So, we solved them to find out the value of n. Okay. The other method, as we learned last time, we use the equations basically, and based on that we derived exactly similar equations basically. So, either you can use that way or you can use this way. Remember last time when we derived the shape functions, we assume they will add up to 1, meaning that any element, let us say 5 noded element, something like this one, 1, 2, 3, 4 and 5, summation of ni has to equal to 1, otherwise there will be a problem. For example, if T1, if all the points have similar temperature, T here, let us say T naught here, 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 then as T xy can be written as n I xy times T I equal to 1 to 5 in this case. So, if T I is equal to T 0, so that means T x, that means T xy will be equal to n I xy T 0 equal to 1 to 5. So, what you get here is T naught and then summation of I equal to 1 to 5 n I xy. Okay. Now, if all the nodes have the same temperature, then if you apply the principles of a heat transfer, then temperature within the plate has to be the same temperature, that is T naught, that should be equal to the same temperature that you find at the nodes. So, here T xy has to be equal to T naught only, and that will only happen when this thing, the whole thing is equal to 1. That is we want that all the nth shape function x y, they converge to 1, okay, equal to 5. Okay. So, we have to make sure that we can if we are using some method and they are not adding up to 1, in that case what will you do? You can find out, let us say you have found out n1, n2, n3, n4, which may be easier to find, and n5 you can assume it is equal to 1 minus n1 minus n2 minus n3 minus n4, and you will that way you will get the fifth shape function. So, it will also make sure the sum of all 5 shape function will equal to 1. So, this is for, of course, I am talking about this one example which has 5 nodes. So, we can extend the same thing for element of any number of nodes. So, another way of deriving the shape function for this 4 noded element will be what is known as tensor product method. This is the same as what we did earlier, however, new perspective. So, if this is a rectangular element, so for bar element, if you remember, we had n1 x, which was 1 minus x over L, and n2 x was x over L. So, let us say for this one, if length from here to here is L, so n1 x as in a 2 noded bar element will be 1 minus x over L, and n2 will be equal to x over L. Similarly, same thing we can do it for the vertical direction. So, let us call it n dash, or call this one n x1, rather n x1 go like this, and this is n x2, and this will be n y1, which is a function of y, which is equal to 1 minus y over h, and n y2 y will be equal to y over h. Now, this is the height h we are talking about. So, our n 1 x y is given by n x1 x multiplied by n y 1 y. So, is equal to 1 minus x over L multiplied by 1 minus y over h. Similarly, n 2 x y. So, n 2 x y. So, for x1 this is the second one, and for vertical one this is still the first one. So, this and this. So, we get equal to n x2 x multiplied by n y1 y, and therefore, it will equal to x over, for this one 1 2 3 4, for node number 2 it will be x over L multiplied by 1 minus y over h. Okay. Similarly, n 3 x y will be equal to n. So, for n 3 this is the second one for both. So, second one for both of them. So, this will be n x2 x multiplied by n y 2 y, which will equal to x over L multiplied by y over h, and last one n 4 x y is equal to, either we can, here you can also write 1 minus n1 minus n2 minus n3, and if you work out you will get this is equal to 1 minus this will be x over L multiplied by this will be 1 minus x over L multiplied by y over h. So, you can also do like this, or otherwise also you can write as we wrote for others, that is n4 xy xy is equal to n x1 x multiplied by n y to y, and what we get is n x1 is 1 minus x over L multiplied by y over h. So, this is the same as earlier. Okay. So, this method is called the tensor product method. So, once we have shape functions, the next thing is to find out the stiffness matrix. And for a stiffness matrix, if you remember, it is for all elements. So, k will be equal to this integration over the whole domain, in this case is area, and then it will be B T transpose of B, then D, then B, and this is integrated over the whole domain, where B matrix is nothing but what determines is, so if T x y, you write it as n summation of n I x y multiplied by T I equal to 1 to 4 in this case. So, dt over dx will be equal to summation of I equal to 1 to 4 and del n I del x T I, similarly del t over del y will be equal to summation I equal to 1 to 4 del n I del y T I, and so this one, the gradient of t will be given by del t over del x del t over del y, right, and which will be equal to, here there will be a B matrix multiplied by T matrix, T vector. So, this will be T1, T2, T3 and T4. So, this is how B is related. So, B related to the gradient of T. So, B is nothing but B is equal to del n1 del x del n2 del x del n3 del x del n4 del x, and here second row will be del n1 del y del n2 del y del n3 del y del n 4 del y. Okay. Okay. And D is a conductivity matrix. So, this one is for isotropic, you can write it as K 1 0 0 1. If it is anisotropic, then all 4 entries may be different. So, D is as given here. So, finally, if we take the derivative, if you know the derivative of n, then we can find out the stiffness matrix. So, if let us say K is composed of say this matrix K 1 1, K 1 2, K 1 3, K 1 4 and so on. So, this will be K 2 1, K 2 2, K 2 3, K 2 4, K 3 1, K 3 2, K 3 3, K 3 4 and then K 4 1, K 4 2, K 4 3, K 4 4. So, K I j we can write it as K I j equal to integration of, we can use the same domain here and will be equal to K, which is conductivity, multiplied by del n I x okay, then del n j x plus del n I y multiplied by del n j del y integrated over the whole domain. How this comes from this relation, the relation this relation. So, what we see is a transpose of B multiplied by D. So, in this case K, D may be taken as a constant and then this B. So, what we will get is the individual entries will be composed of this one. So, if you do not agree, let us see in details why it should be like this one. So, what I said is B, we know that K is equal to this one B T D B integrated over a whole domain. If D is equal to K 1 0 0 1, then we can actually take K instead of D. So, you can write K also as equal to B T B D omega and here multiplied by K. So, that will be now if we individually see B transpose B, that will be equal to like this. So, del n1 x, del n1 n2 x, n3 x, n4 x and similarly del n1 del y, del n2 del y, del n3 del y, del n4 del y. So, then multiplied by B. So, the B will be here. So, again the same this is n1 del x1, n2 del x, and here del n1 del y, the del n2 del y, and so on. We will have like this. So, if we just find the let us the entry at 1 1. So, this the whole thing will be this the first is 4 by 2 matrix, the second is 2 by 4 matrix. So, the whole thing becomes 4 by 4 matrix, and the first one will be first entry of this 4 by 4 matrix will be this multiplied by this one. So, what we get is del n1 del x multiplied by del n1 del x plus del n1 del y del n1 del y. Now, here the second entry in the first column or the first entry in the second row will be this multiplied by this one. So, del n2 del x multiplied by del n1 del x plus del n2 del y multiplied by del n1 del y. So, that really means that simply k I j will be equal to integration over the whole domain k, and there will be del n I del x del n j del x plus del n I del y and del n j and del y, whole of it integrated over the whole domain as I wrote earlier. So, let us say if in order to find out k 1 1, so if we find out k 1 1, so this will be equal to k, we write k inside omega, k could be a variable also. So, this becomes del n 1 del x square plus del n 1 del y square. So, this is how it will look like, the omega, and remember our element here is rectangular and length is like this and height is like this one. So, domain here is this rectangular area, where area is equal to L times h, and x varies from 0 to L and y varies from 0 to h. So, accordingly k 1 1 we can write it as equal to k, and rather for any I j we can write. So, k I j becomes equal to this is k conductivity. So, 0 to h for y we are writing, 0 to L we are writing for x, then k, and then we have del n I del x del n j del x plus del n I del y del n j del y, and here it will be dx dy. Okay, so for k, so here I repeated k, so I removed the 1 k, the conductivity. So, k I j now let us say k 1 1, if I want to find out, will be equal to 0 to h, 0 to L, del n 1 del x square plus del n 1 del y square and dx dy. Okay. So, we have to find out del n 1 del x del n del n1 del y as well, both of them. So, n1 we know that this is equal to 1 minus x over L multiplied by 1 minus y over h. So, del n1 del x will be equal to minus 1 over L 1 like this, and del n1 del y be equal to 1 minus x over L multiplied by minus 1 over h. So, this is how we can find out. Okay, so we get del n1 del x square plus del n1 del y square becomes equal to 1 over L square 1 minus y over L square, and similarly you get plus 1 over h square and 1 minus x over L square. So, once we have the del n1 over del x square plus del n1 over del y square. So, we can find out k11. So, k11 will be equal to k11 is equal to, so we are assuming conductivity k to be a constant. So, this is k, and then 0 to h, 0 to L, and then here we have del n1 over del x square. So, del n1 over del x square becomes equal to 1 over L square multiplied by 1 minus y over h square, and then we have del n1 over del y squared. So, here we have 1 over h square and 1 minus x over L square, whole thing integrated domain is for the whole area. So, this we can separate because this is only function of y, this is only function of x. So, we can write it like this one. This is equal to, so k, so k 0 to h, 0 to L square 1 minus y over h square dx plus k 1 over h 0 to h, 0 to L, and then 1 over h square 1 minus x over L square, here y dy as well. So, dx dy. So, the first one is function of y, so we can write k and then 0 to h, k over L square, take L square out, and then 1 minus y over h square dy, and then 0 to L dx, okay, because there is no x variable. So, I can just write it like this, and then we have plus k over h square and 0 to h dy and 0 to L and 1 minus x over L whole square and integrated over from x equal to 0 to L. Okay, so the first one becomes k over L square times 1 minus y over h cube over 3 multiplied by minus 1 over h, okay, and the whole thing is from 0 to h, and the second term is k over h square. Okay, so this term also we should write, so this will be simply equal to L, so we write L here. So now the second term, this one, so k over h square, and then first term, this term is multiplied by h simply, and second term same as same form as this, so 1 minus x over L cube divided by 3 minus 1 over L. Again it goes from L to 0. Okay. So we can write k11, we were calculating, so k11 equal to the first term, we expand, so we get k over L square multiplied by L multiplied by minus h over 3 multiplied by 1 minus y over h 3 h to 0, and similarly the second term will be plus k over h square times h times 1 minus L over 3 multiplied by 1 minus x over L cube and 0 to L. So becomes k over L minus h over 3, and then this term, so if you put value h here, so this becomes 1, this becomes 1, so 1 minus 1 becomes 0, so this whole thing becomes 0, then minus, and this is 0, then this becomes 0, the whole thing becomes 1. So answer, the value of this is nothing but minus 1. So we write minus 1 here. Similarly, for second case also we get k over h multiplied by minus L over 3, and the whole thing, this one is equal to minus 1. Yeah, so this we write here also, this is minus 1 multiplied minus 1. So the value we get is equal to k h over 3L, and here we get k L over 3H. Okay, or simply we get k over 3 and here we get h over L plus L over h. So this is what we got k11. Similarly, we can find other components like k12, k13, k14, etc. Note that k11 is equal to k22, will be equal to k33, will be equal to k44. This is because this is a rectangular element and all these four nodes are actually interchangeable, meaning that they are symmetric about this horizontal line and vertical line. Because of this symmetry, there will be other components which will be equal. So let's number it first, 1, 2, 3, 4. So k12 will be equal to k21, should be equal to k34, will be equal to k43. Similarly, k 1 4 will be equal to k 4 1 should be equal to k 2 3 should be equal to k 3 2. Okay. Similarly, k 1 3 will be equal to k 3 1 should be equal to k 2 4 should be equal to k 4 2. That really means we have to only determine only 4 components. That means if we know k11, we already know 3 others. If we know k12, we also know 3 others. Similarly, if we know k14, we will know all these 3, and k13, if we know all these 3 as well. So that means we have to only determine only 4 of them. Furthermore, what we observe is 1 2 and 1 4, k12, if we know, we should be able to determine k14 based on this one by interchanging L and H. This is based on the fact that if L, which is the length between nodes 1 and 2, and H, which is the length between nodes 2 and 3, were the same, then k12 should be equal to k23. So let's find out k12. So k12 should be equal to k and then del n1 del x del n2 x plus del n1 del y plus del n2 del y, and all of it integrated over the whole domain, so omega here. So that is equal to we have del n1 over del x, we have determined already, so that is equal to minus 1 over L and then 1 minus y over h del n1 y is equal to 1 minus x over L multiplied by minus 1 over h del n2 del x will be equal to 1 over L 1 minus y over L del n2 del x will be equal to x over L and then minus 1, here it will be h, so over h, like this. The value k12 will be equal to k12 will be equal to, so 0 to h, then 0 to L, and then we have del n1 del x times del n2 del x, so will be equal to minus 1 over L square 1 minus y over h, there will be k term here, so will be plus the second term is will be this n2 sorry, this it n2 del ny, so plus 1 minus x over L multiplied by x over L multiplied by 1 over h square, so we got this term, so total, so this is equal to, we have k and then k, then 0 to h, and then we have minus 1 over L square on my so make sure this is correct. So this is has to be a square, so 1 minus y over h square dy times 0 to L dx term will be there, plus k 0 to h term dy, okay, and then 0 to L term, and you have 1 over h square and x over L, 1 minus x over L dx term. So finally we should have equal to minus k over L square and 1 minus y over h cube over 3 minus 1 over h term, and the whole thing is from h to 0 times L, and plus k over h square times h, and then you have x over L, so x square over 2L minus x cube over 3L square, and the whole thing from L to 0. So final value we get equal to minus k L square, and this value from here we get minus h over 3, and this h we put, we get h we put here, we get 0, and if we put 0 we get 1, so the value becomes minus 1 times L plus k over h, and here we get L square over 2L, so L over 2 minus we get L over 3. So this is the value. So final value we get equal to, so here is minus 1, so we get here minus plus and minus here, so minus k h over L 3L, so k h L, and minus term is here over 3, and this term is L over 6 term here, so k get k L over 6h. So this is the term we get. This one is k12. Now if you see here, this is node 1, this node 2, this node 3, this node 4. So k12 can be determined from k23 can be determined from k12. How? By just interchanging L and H. So k23 or k14 Yeah, so let's write k14. So k14 will be given as, we will just interchange it, so you get minus k l over 3h plus k h over 6l. So this is what we will get. We have now k11, k12 and k14. So can you find out k13? K13 can be found out the usual way, the way we have found out all k11, k1, k12. However, we will use some other trick. So you know that if you add k11 plus k12, k13 plus k14, all should, we see that they should add up to 0. We have been doing in the class always, so same logic here. So k13 will be equal to minus k11 minus k12 minus k14, and here k11, if we see here, so k11 is this, k over 3 h over l, l plus s, so we have k over 3, okay, then l over h plus h over l, then it will be minus, then k12 is this one, so minus, so this becomes plus kh over 3l minus kl over 6h, okay, and then k12, so k into this one, so becomes plus kl over 3h and minus kh over 6l. So when you simplify this, whatever the value is will be the value of k13. Hence we have seen that everything is known now. So as we analyzed earlier, if you know k11, you know 3 others. Similarly, k12 knowing, automatically 3 more is also known. If k14 is known, the other 3 is also known as, and similarly for k13. So that means we have determined all of them already. So to summarize, we have k11 which is equal to small k over 3 multiplied by l over h plus h over l. Then we have k12 which is equal to minus k over 3 h over l plus k over 6 l over h. Then we have k13, when you work it out, this will be equal to minus k over 6 and then l over h plus h over l, and k14 which will be equal to minus k over 3 l over h plus k over 6 h over l. So this we have determined. They also determined this. We got from k12 by interchanging h and l, and k13 we got by making k11 plus k12 plus k13 plus k14 equal to 0. So k13 we got by making k13 equal to minus k11 minus k12 and minus K14. So this is what we'll get automatically. So the original element is given here 1 2 3 4, and as I mentioned earlier, here this is L, here this is H, and we have K1 is equal to K22 equal to K33 equal to K44. Okay, then K12 equal to K21 is equal to K34 equal to K43. Then K13 is equal to K31 is equal to K24 equal to K42. This is all because of the symmetry. Then K14 is equal to K41 is equal to K23 equal to K32. So we already have values for K11, K12, K13 and K14 as given here. So our matrix Bk is given by K11, K12, K13, K14, K21, K22, K23, K24, K31, K32, K33, K34, K41, K42, K43 and K44. So this is the stiffness matrix 4 by 4, where the values of Kij can be got from these identities and these values. So this is the final expression for the stiffness matrix for a 4-noded element.